APEX department at the Max Planck Institute for Astronomy stands for Atmospheric Physics of Exoplanets. And the idea of the department is that we are a one-stop shop for all things exoplanet atmosphere characterization. So we do observations of exoplanets from the ground and also with space telescopes. We build theoretical models of atmospheres in both 1 and 3 dimensions. We also build purpose-built instruments to characterize the atmospheres of the planets at the next level of detail. As I mentioned, one of the things that we're really excited to work on in the APEX department is data from space-based telescopes. And one of our really exciting science results from the year 2023 was the direct detection of thermal emission from a small rocky exoplanet called Trappist 1c.
So we pointed JWST at Trappist 1. Trappist 1 is an exoplanet host star, which has 7 Earth-sized exoplanets in it, and 3 of them are in the habitable zone, so where you can have liquid water on the surface. And because of that, it's really interesting for scientists and also for the general audience. And we looked at Trappist 1c, which is the second planet in the system. And the really interesting thing about Trappist 1c is that it's basically a Venus twin. If you look at its size, its mass, and also the amount of flux it receives basically from its host star. And the idea was then to basically compare the atmosphere which you have on Venus with the atmosphere observed with Trappist 1c. And what we basically observed was so-called secondary eclipses. During a secondary eclipse, basically the planet disappears behind its host star, and what you basically see is a small dip in the amount of flux you observe. And that dip is basically caused by the planet basically disappearing behind its host star. And any amount of flux which is basically emitted from the dayset of the exoplanet suddenly disappears. And from that you can calculate its temperature, and this temperature basically can then be converted into possible atmosphere. And so we basically compared this temperature with possible atmospheric scenarios, and we saw that the most consistent atmospheric scenario was either the planet having a really, really thin CO2 atmosphere or the planet having no atmosphere at all. In the end, we really want to figure out how common an Earth is. First step for that is to figuring out how common atmospheres survive on rocky exoplanets. We don't know that yet. We know that rocky exoplanets are really common in our Milky Way. We know something generally about their composition. And so this is like really the main thing JWST wants to answer: which kind of atmospheres these rocky exoplanets have, and how often do atmospheres survive on rocky exoplanets. The great thing about APEX is that we have a lot of knowledge about the characterization of exoplanets here, and especially on rocky exoplanets. And one thing which we will definitely do with JWST is to further characterize the surface of rocky exoplanets. Another thing is that we also want to figure out how big rocky exoplanets can get. And so we want to really explore this transition region between big rocky exoplanets and, on the other hand, small, basically mini Neptunes. So Trappist 1c is outside of the habitable zone. In the future, we want to push further towards the habitable zone. So with Trappist 1d and e, for example, where Trappist 1e is probably one of the most Earth-like planets out there, looking at its size and the amount of flux it gets from its host star. So characterizing these 2 planets, D and E, would be a future goal for sure. And we will basically try to observe the planets in the same way as we observed Trappist 1c, in order to figure out if it's a bare rock or if it has maybe a thin atmosphere.
And it's not only rocky planets we're interested in. We're also interested in larger planets more similar to Uranus and Neptune, or even Jupiter in our own solar system. We're also interested in the physics of the planet atmospheres and how they work in 3 dimensions, how heat is circulated, what types of clouds and hazes form. And our resident expert in modeling the 3D-ness of exoplanet atmospheres is our postdoc, Maria Steinrück.
Hot Jupiters are the size of Jupiter, and they also have a similar composition, so their atmosphere is mainly made of hydrogen, but they're much, much closer to their star, much closer than Mercury is to the Sun. And because of that, they're tidally locked, so one face of the planet constantly faces the star, and the other side of the planet is basically an eternal night side. And mini Neptunes can basically be anything, but most of the ones that we study right now are also very close to their star. What's more challenging with mini Neptunes is that we don't really know what their composition is like. They could be still mostly hydrogen dominated, or they could also have atmospheres that are more made of water or CO2. We don't have a planet like this in our solar system. So the way I study them is with 3D computer simulations that run on a supercomputer. And they are basically a climate model that simulates the temperatures and the wind everywhere on the planet. So the most exciting project that I've been a part of here during my time at Apex was a measurement of the phase curve of a mini Neptune called GJ1214b. It has a very thick cloud or haze layer, and that basically hides the signatures of the molecules that we see. So basically we measured this day to night temperature contrast, and this was the first time this measurement was done for a mini Neptune. So it was super fun to be part of that, and I ran all of the climate models that we compared with the observations. This cloud or haze layer is very reflective, and the planet has a very high albedo, and that's something that none of us really expected. We thought it would be relatively absorbing clouds or hazes. Okay, so we're now in an era where we really for the first time can really begin to measure the detailed composition and physics that happens in the atmospheres of these planets. A bit like planetary science in the time of the Voyager missions. We're now in that same period for exoplanets, thanks to all of these great new telescopes.
Exoplanet atmosphere characterization is really difficult. The signal from the planet is very small compared to the glare of the host star. And to really push down and measure the physics of the atmospheres and learn about planets more similar to Earth, we need the next generation of instrumentation. And Paul Moliere, one of our staff scientists, has been working on developing the science case for a future instrument for the ELT called ANDES.
So ANDES is going to be an instrument for the Extremely Large Telescope, which is one of the was the biggest upcoming ground-based telescope that we are all waiting for. It has a 40-meter sized mirror, and the mirror of course is great for seeing lots of interesting things that are faint in space, but you actually have to have an instrument to make sense of these measurements. In this case, what's happening is that the light is going into the ELT, hitting the mirror, and then going to the ANDES instrument, where we'll take a really high resolution spectrum of the stars and planets that we want to study. Building an instrument such as ANDES is a huge undertaking, so there's many different people involved in this project. My part is modeling the signals of exoplanets that we want to observe. For example, in ground-based observing, which ELT is going to be with ANDES, we often used one-dimensional exoplanet models, but this is not going to cut it anymore in the future, so we actually had to develop three-dimensional models and use these to predict what the science output of ELT could be. But having this high signal and having this high resolution really allows us to trace winds in planetary atmospheres, really map the dynamics of these planets, even draw maps of their surface brightness basically, so you can really, in a sense, take a picture of a planet, although we can't actually resolve it. So can we, with ANDES, maybe start putting some constraints on planets that are in the habitable zone? Are they maybe inhabited? Do we see biomarkers, or do we maybe see anti-biomarkers that help us to exclude life on these planets? So this is all science that ANDES will enable, and yeah, I'm looking very much forward to it.
The future of the field of exoplanets is extremely bright. We have new planet discoveries coming up, new missions, new telescopes, loads of new data, and my dream for the Apex department is that this will be the place where we can work out these problems and challenges together, and ultimately, finally push towards our goal of discovering evidence for life on an alien world similar to our own.